I will present our paper, Gradient-Based Uncertainty Attribution for Explainable Bayesian Deep Learning. This is a drawing work of Hanjin Wang, Jia Zhaxi, Shixiang Wang, and Qiangji. This is also a collaboration work between RPI and IBM. First, let's have an introduction to the uncertainty attribution. So uncertainty quantification is very important, especially for some safety critical applications. And we basically use Bayesian neural networks to quantify uncertainty. Bayesian neural networks treat parameters as random variables and compute the posterity distribution of the parameters. It provides a well-founded framework for uncertainty quantification. After we have quantified uncertainty, we can show some inputs have high uncertainty, so we know there's something wrong with those inputs. But we are not know where it's wrong or why it's wrong with the input. This work focuses on uncertainty attribution, which try to understand and explain the sources or causes of uncertainty. Basically, we want to localize the high uncertainty regions to determine where it's wrong. It is not a well-explored area, and previous methods, especially for some explainable AI method, focusing on attribution of the classification scores of the deterministic models. So first, let's have an overview of our method, UA backprop. You can see we first do a forward pass of the Bayesian deep learning models to quantify the uncertainty. Three types of uncertainty are quantified: epistemic uncertainty, aleatoric uncertainty, and total uncertainty. Then we do a back propagation step from the uncertainty to the input to find the contribution of each pixel to the uncertainty so that we end up with the uncertainty map to show where it's wrong. These back propagation steps are specially designed. First, we focus on gradient-based method. We want to finish the attribution within a single backward path. And the attribution maps should also achieve the completeness property. And we also want the gradients to be smoothed so that we can have a clear visualization. So to talk a little bit more, let's show some details of the UA backprop. We have 4 steps. First, we do a forward pass. Since the exact posterity distribution are really hard to calculate, we can have some samples from the posterity distribution. And then we can have multiple outputs. And then we can use those outputs to quantify uncertainty. Since we are focused on classification problems, the uncertainty can be quantified by the entropy and the mutual information. Once we have the uncertainty, we do a back pass from the uncertainty to the softmax probability. So the goal of these steps is to find the contribution of each GI, each softmax probability to the uncertainty. Based on the linear relationship here, so each individual contribution can be easily get. Then we do a back propagation step from the softmax probability to the logits, G to Z. The goal of this step is to find the contribution of each Zi to U by exploring all possible paths from Gj to Zi. So you can see here the contribution of each Zi to the uncertainty is the aggregation of all possible paths. So each coefficients here are quantified by the gradients, specially designed gradients. So finally, we do a back propagation step from logits to the inputs, and combined with previously, we can really find the contribution of each pixel to the uncertainty by exploring the whole path here. If you want to know more about the equations, you can refer to our paper. So for the evaluation, we first do a qualitative evaluation to show where it's wrong. You can see when we have the input images, those images have high uncertainty, and our method can provide a clear visualization to show where it's wrong. For example, this one, for the 3, it may indicate that the tail here that caused this original 3 to have a high uncertainty. We also consider several quantitative evaluations. First is blurring test. The idea is that we want to iteratively blur up to 2% or 5% of the image pixels following the order of high uncertainty attribution score. Basically, we will blur the problematic regions and analyze the uncertainty reduction curve. two metrics are designed. One is called maximum uncertainty reduction rate, and one is called area under the uncertainty reduction curve. On average, we show that our method can achieve the best performance compared to state of arts. We also consider anomaly detection. This process shows that we will synthetically create the ground truth parametric regions by replacing one patch of the original image by one patch from other images. And we can also use our method to detect the parametric regions and compare the two bounding boxes. So the IOU are provided, which is the area of the overlap divided by the area of union. More visualizations are provided here, and we also show some quantitative results to show that our method can achieve the best performance compared to state of arts. So finally, we also consider an uncertainty mitigation strategy to use uncertainty attribution maps as attention. So the idea is that given uncertainty attribution map MX, we can design attention maps to strengthen more informative regions by ignoring the unimportant background information and ignoring the parametric regions. You can see here is once we have the attention maps, we can use the attention maps to weight the latent features of the original image. And finally, the weighted features can be used for a classifier to gain better prediction. The accuracy and negative log likelihood for the uncertainty mitigation evaluation are provided, which also shows that our method can achieve improvements over the state of arts. Thank you for your listening.